Welcome back everyone. In this video, we'll be solving few problems from the chapter Kinematics and Relative Motion. The level of the problems would be moderate, and so you guys also solve along with me and comment down below how many you got correct. And if you enjoyed the video, please like and subscribe and also share it with your friends. Okay, so let's begin with problem number one, starting with an easy problem. So a particle's velocity is given to be this, and we have to find the magnitude of tangential, normal, and total acceleration at this particular time. The velocity vector is given to be ai cap plus bt j cap. Okay, so if I differentiate this, I'll get the acceleration vector as b j cap. So now if I just plot a rough sketch of the velocity vector, it will be something like this. And let's say it makes an angle theta with the x-axis. And also the acceleration is b along the y-axis. So the acceleration vector is something like this. So now the tangential acceleration is going to be the component of acceleration along the velocity vector. That is going to be a sine theta. So now how do we find theta? So theta, we know the x component of velocity is going to be a, and the y component of velocity is going to be bt. So tan theta from this triangle is going to be bt by a, and they were asking at the time of a root 3 by b, you'll get tan theta to be root 3 and theta would be 60 degrees. So the tangential acceleration is going to be b sine 60, which is root 3 by 2. So this is going to be the tangential acceleration. Okay, and the total acceleration is simply going to be p. So the normal acceleration is going to be square root of the total acceleration squared minus the tangential acceleration squared. This would turn out to be b by 2. So the answer for this question is option A. So this is problem number 2 for the day. And this is a pretty unique problem. So we are given a particle that is projected from the ground, okay, in the Earth's gravitational field at an angle theta with the horizontal. At the Earth's gravitational field at an angle theta with the horizontal. Okay, so let's draw a diagram. Okay, so they're saying the center of curvature at the topmost point. So this is going to be the radius of curvature at the topmost point. So let's try to find that. So if it is projected with an angle theta, the velocity at the topmost point is going to be v cos theta. And the perpendicular acceleration is simply g downwards, right? So the radius of curvature at the topmost point is going to be v squared cos squared theta divided by g. And the question, we have to make sure that this center point C comes below the ground. So how can we do that? Well, so let's say for some other theta, the projectile was something like this. And for this particular case, let's say the center of curvature is below the ground. Okay, so the only thing that we have to do is, so this is going to be the radius of curvature of this circle. If this is greater than the maximum height of the projectile, then can you see the center of curvature will be below the ground? And that is exactly what we'll be doing. So this is going to be the h max of this projectile, and this is going to be the radius of curvature at the topmost point. So as you can see, the radius of curvature, if we make sure that the radius of curvature at the topmost point is greater than the maximum height of the projectile, then we can ensure that the center of curvature is below the ground. So the radius of curvature at the topmost point, we determine it to be v square cos square theta by g, and this should be greater than h max of a projectile is u squared sine squared theta divided by 2g. And from here, we'll get the value of theta should be less than, which would be option A. Okay, moving on to problem number 3. So we have an observer O who is sitting on an accelerated trolley. Okay, so the observer O is sitting in this trolley, which is being accelerated with some acceleration A in the xy plane, which we don't know about. And he is observing a projectile Q of mass 5 kg moving under uniform gravitational field of Earth, acting towards negative z-axis. If I take this to be the x-axis, and let's say this is the z-axis, so the gravity in this particular coordinate axis, the gravity will act downwards. So this guy on the accelerated trolley observes a momentum p of the particle to be this. So we have to find the acceleration of the trolley at t equal to 2 seconds. Okay, so the momentum vector is given to be 15 t I cap minus 10 t squared j cap minus 50 t k cap. So if I differentiate this vector dp by dt, we'll get the force observed by this man on the trolley, and that would be 15 I cap minus 20 t j cap minus 50 k cap. So now as the time is given to be 2 seconds, okay, so this is the force that the man observes. So with respect to this guy on the trolley, this Q will have two components of forces, right? One is going to be the weight of this body, and that is going to be 5 into g, which is 50 Newton. And one, we have no idea about it, but in some direction, a pseudo force. Okay, now this 50 Newton is along the minus k cap direction. Okay, so this direction is minus k cap, will be because of two components. One is F pseudo, other is the weight of the mass, right? So from here we'll get the pseudo force to be 15 I cap minus 40 j cap. Now now the magnitude of pseudo force is the mass of the particle q, which is 5, times the acceleration of the trolley in which the man is traveling, and this would be 15I minus 40j. And from here the acceleration of the trolley 3I cap minus, that would be option B. Moving on to the next problem. So we have a projectile that is fired with a velocity v at an angle theta. So the question is, what would be the radius of curvature of the path at the instant when the rate of change of speed of the projectile is minimum? Okay, so they're saying rate of change of speed, which would be d mod v upon dt, is minimum. So during projectile motion, let's say at some general instant, at some general point P, if we draw the velocity vector, and let's say it makes an angle, the gravity will act in the downward direction, and let's say the velocity vector makes an angle theta. So here d mod v by dt, which is the tangential acceleration, is going to be, this will be 90 minus theta. So the tangential acceleration is going to be g sine theta, but there would be a minus sign because the speed is decreasing, right? Okay, so now at which instant will sine theta be minimum? It will be minimum when theta is minimum, which is actually at the topmost point, right? Because at the topmost point, the velocity is completely horizontal. Or you could say the tangential acceleration is 0 at the topmost point. And we know at the topmost point, the velocity of the projectile is v cos theta, and the acceleration perpendicular is g. So from this, we can get the radius of curvature at the topmost point to be v square cos square theta divided by g, which would be option A. Moving on to the next problem. On one boundary of a swimming pool, there is a person at point A whose speed of running on the ground is 10 meters per second, while that of swimming is 6 meters per second. He has to reach a point B in the swimming pool. The distance covered on the boundary, so that the time required to reach the point B is in the pool is minimum. So in this problem, we'll be using a result that I derived in one of those previous videos. It's like whenever two medias are separated by a boundary in which the velocity with which a body travels in medium 1 is v1, and let's say the velocity with which he travels in medium 2 is v2, and we have to go from a point A to a point B in minimum time, keyword being minimum time. We just have to think of what will light do in this situation. And light, we know, as it undergoes a refraction at the interface of the media, it follows Snell's law, right? So if I say this angle is alpha and this angle is beta, so we can say v1 upon sine alpha is equal to v2 upon sine beta. So we'll be using this result in this problem. Now the point B is over here. So the distance of 4 meters from the interface. Okay, if it takes minimum time to reach from A to B, then it should also take minimum time to reach point A from point B. Let's say light starts its journey from point B. So let's say it reached the interface at some point here, and then it has to travel this much distance to reach point A. So as you can see, if this angle is theta, this angle is theta, and this will be 90 degree. So this problem is basically, I mean, if any of you have learned optics, it's just we just have to find the angle at which TIR happens. So anyways, like applying Snell's law at this interface, speed of swimming. So the speed of swimming is given to be 6 meters per second divided by sine theta is equal to the speed of running, which is 10, divided by sine 90, which is 1. So from here, we'll get the value of sine theta as 3 by 5. Okay. Now in the problem, they have asked the distance covered on the boundary is C. So we have to find the distance AC. Let's say this point is D. So the distance CD is simply going to be 4 tan theta, and that is 3 meters. So the distance AC, now AD is 10. So distance AC will be 7 meters. So option C is the right answer. Next problem. So we have a particle that starts from the origin. It accelerates for the first t0 seconds, and then decelerates with the same acceleration till 2t0 seconds. So the point starts from the origin, which is x equal to 0 in this case, and it starts and the particle starts accelerating till t equal to t0, which means it must have gained some velocity at this point, and then it starts decelerating. So its speed, so it will still continue on this path, but its speed will decrease, and when it reaches 2t0, it will come to rest. We have to draw the graph in this situation. So first and foremost, the displacement is always positive. The displacement from the origin is always increasing, right? It is not decreasing. It will only decrease after the time 2t naught, because after this the particle will start moving towards the negative x-axis. Displacement is always increasing, which means option A and option B are wrong. As we know, the acceleration is dv by dt, and velocity is the slope of xt curve, right? So as you can see, the slope here in this part is increasing, and after this point the slope is decreasing. So option C will be the right answer. In this case, the slope is increasing, and here also it is increasing, so this would be the wrong answer. Okay, or you can also do it by checking the concavity of the curve. Moving on to the next problem. So we have an incline in this case, which is inclined at an angle 30 degree to the horizontal. We need to find the horizontal velocity v naught with which the particle must be projected from this point so that it hits the inclined plane perpendicularly. So the velocity must be in this direction, and the angle is it must make with the vertical should be 30 degrees, right? Because the incline makes an angle 30 degree with the horizontal. Now, as this velocity vector is normal to the inclined plane, it must make an angle 30 degree with the vertical. So we'll be using the kinematic equation v equals u plus gt. To the initial velocity vector, if we add a gt vector, we'll get the final velocity, right? So the initial velocity is it's v naught, and to it, if we add a gt vector, we should get the final velocity, which would be this, using simple vector addition. And we know the final velocity vector makes an angle 30 degree with the vertical, which means it should make an angle of 60 degree with the horizontal. Okay, and from this triangle we can say tan 60 equal to gt divided by v naught, and from here the time comes out to be root 3 v naught divided by g. So this is how the diagram of the situation looks like. So let's just say for a moment that this distance is r. So from this diagram, draw a horizontal line at this point. We can say this angle is 30 degrees. So this would be root 3 r by 2, and this distance over here would be r by 2. So this height is now h minus r by 2. So first and foremost, as the vertical velocity at this point is 0, so if you simply use kinematics equation from between these 2 points, we can say the time of flight is root 2 times h minus r by 2, which is the height of fall, divided by g. So let's do that. So square root of 2 times h minus r by 2 divided by g, and this would be equal to the time which we just found out, that is root 3 v naught divided by g. This would be our first equation. As we also know the horizontal displacement of the particle, root 3 r by 2, and this would be, as there is no horizontal acceleration, we can just write it as speed multiplied by the time taken, which is root 3 v naught by g. Okay, so now let's substitute 2 in equation number 1. So v naught square comes out to be 2gh divided by 5, which would be option A. Next problem, a small particle of mass m is projected at an angle theta with a velocity v naught. So at a time t less than v naught sine theta by g. So this is the time it takes to reach the highest point, right? The total time of flight is 2 v naught by g, 2 vy by g. This time is vy by g. So we have to find the angular momentum of the particle at some general time which is less than this. Okay, so for people who don't know what angular momentum is, you can basically just define the angular momentum of a particle about a point as simply the r vector to that point cross the momentum vector. Okay, so if this is our projectile, one way of doing this problem is that you find the r vector as a function of time, find velocity as a function of time, and just do cross product of them, and you'll get the angular momentum. The much simpler way is to find the torque of this particle about the origin. So the torque of the particle about the origin is going to be, so there is only one force that is acting on the particle, and that is the force of gravity, whose magnitude is mg, and the perpendicular distance from the origin is going to be x, right? So the torque about origin is going to be mg multiplied by the perpendicular distance from the axis, which is x, and x as a function of time, we can write it as v naught cos theta t, and its direction will be, in order to find the direction, you have to do r cross f. So if you do r cross f, you'll get the answer as into the plane, which would be minus k cap in this case. So now you have torque as a function of time, and torque is also defined as the rate of change of the angular momentum vector. All you have to do is integrate this torque expression to get the angular momentum. and that be mg v naught cos theta, because all these terms are independent of t. It would be t dt, and integrate it from t equal to 0 to t equal to any general time t. And if you integrate this, you'll get the answer as this, which would be option A. Moving on to the next problem. So in this question, we have a stone that is projected from a horizontal plane. So it attains a maximum height of h and strikes a stationary smooth wall and falls on the ground vertically below the maximum height. So we have to assume the collision to be elastic and the height of the point of wall where the ball strikes. Okay. So, and it's given that after the collision, the ball, now as is an elastic collision, so let's assume for a moment that the wall didn't exist, so the projectile would continue on its path. So if the wall wasn't there, the projectile would have continued its original path. But as now, as the collision is elastic, these two parts of the projectile are exact mirror images of each other. Why is it like that? Because at this point, the horizontal velocity was like this, and it is v naught cos theta, right? And the vertical component is v naught sin theta. Now after collision, what will happen? The only thing reversed is the v naught cos theta. The vertical velocity remains unchanged. Okay, so as the only component that is changed is v naught cos theta, this part of the motion and this part of the motion will be exactly similar. So let's say this distance is x, which means this distance will also be x. Okay, and from here we'll get the value of x to be r by 4, where r is the range of the projectile. So in this particular case, we have to find this. So the coordinate of this point is going to be 3r by 4. If we consider the origin to be over here, the coordinate of this point will be 3r by 4 comma h. Now if we use the trajectory equation, so substituting for the value of h, y value will be h, and the coordinate of x is 3r by 4. So this would be 3 by 16 r tan theta. Now for a projectile motion, the ratio of its range to its maximum height is actually equal to 4 upon tan theta. From here, you can see r tan theta is simply 4h. So if I substitute it over here, I'll get the answer as 3h by 4, which is option C. Moving on to next problem. So in this question, we have been given a river that is flowing with the velocity of VR, and the width of the stream is W, and the velocity of the boat with respect to river is given to be VBR. It's also given that the velocity of the boat relative to the river is actually twice the velocity of the river. So in that case, 100% the minimum drift would be 0, right? Because let's consider, because there would clearly be a case in which the boat, let's say it starts traveling in this direction. The river velocity will obviously be in this direction towards the right. And let's say this angle is some theta. There will clearly be some value of theta for which VBR sine theta would be equal to VR, and in this case the net horizontal velocity would be 0, and the boat with respect to ground will travel in this direction. So there is clearly a possible case. It is only when the velocity of the boat relative to water is less than the velocity of the river stream in which zero drift is not possible. So, and they're asking the corresponding value of theta. So let's just, if we try to find sine theta, it would be VR divided by VBR, which is actually half, and which would mean theta is 30 degrees. So from the horizontal, so from this direction, the angle is going to be 120 degrees. So option B is the correct answer. So now coming to the last problem for the day. So if you guys enjoyed this session, please give it a like, and also give me more recommendations as to, do you guys need the problems to be of higher level than this or almost of the same order? Moving on to this question. So in this question, we have a plane that is flying at a speed of 720 kilometers per hour with respect to air, and the wind is blowing at a speed of 54 kilometers per hour from west to east. Now, with respect to ground, the plane is found to be moving northwards. In which direction is the plane heading? So let's say the plane is here at point P. Okay, so it's given that the velocity of the plane with respect to ground is in the northwards direction. So it is something like this. So this would be velocity of the plane relative to ground. It's given that the wind is blowing at a speed of 54 kilometers per hour from west to east. So the velocity of the wind, so the wind velocity is towards in this direction, and its magnitude is 54 kilometers per hour. So we have to find in which direction the plane is heading. So the velocity of the plane relative to ground is the vector addition of the velocity of the plane relative to wind plus the velocity of the wind relative to ground. So which basically means the velocity of the plane must be along this direction. Okay, it must be in this direction. Why? Because this is the velocity of the wind relative to ground. If you add the velocity of the plane relative to wind, you should get velocity of the plane relative to. So this is going to be velocity of the plane relative to, which basically means this is the direction in which the plane is heading. So now this angle can be easily found out because velocity of plane relative to the wind is given. This is given to be 720 kilometers per hour. So from this diagram, I can write cos theta as 54 divided by 720, which comes out to be 3 by 40. So A option is that it is at a northwest angle. So basically it makes an angle of theta. So it is theta degrees north of west basically. A option says that it is sine inverse of 3 by 40. Okay, so if this angle is alpha, then alpha is going to be sine inverse of 3 by 40. A option says that it is sine inverse of 3 by 40 to the north, which is correct. So A option would be the answer to this problem. So I hope you guys enjoyed this session. If you enjoyed it, please like and subscribe. It takes a lot of time from my side to make these videos. So please do share it with your friends. And yeah, thanks for watching.